So, and we try something today which will probably go wrong, but we want to show you an idea, and that's an idea of how to lead discussions computationally. And I would like to start with a very short example here of how discussions are often led today. And this is a discussion, this is on the BBC, and it's a discussion in a panel, and one of the speakers is a celebrity scientist in the UK, Brian Cox, and he discusses climate change with someone from Australia who says there is no man-made climate change. And I'd like you to look for a moment at this short video, and then we'll see what's going on, if I can start it.
This is now a clear global problem. The absolute consensus is that human action is leading to an increase in average temperatures. Absolute consensus. I know you may try to argue with that, but you can't.
No, not in my
But therefore, but the key point is, can we respond to it? Do we have the political institutions and the political will and the organisation globally to respond to this challenge? And that worries me immensely. I don't think we do at the moment.
And I'm absolutely stunned that someone who is inspired by Richard Feynman, a fantastic scientist who believes in empirical evidence, is quoting consensus.
Can I just say, I brought the graph, right? I mean, can I just...
First of all, that the data has been corrupted, and we know that the 1930s were warmer than today.
Yeah, corrupted. What do you mean corrupted?
Been manipulated
By who?
By NASA. By the
NASA?
yes. As far as I'm concerned, politics should be based on empirical evidence. All policy should be based on empirical evidence. I've heard consensus, which is not science. I've heard appeals to authority, which is not science. I've heard various illusions.
Hang on.
I've heard. Hang on. Hang on, Brian. You showed me a graph.
Okay, that's basically it. So my problem when I saw this and when I see lots of discussions is that actually on neither of the two sides there was any evidence. There was no data, there was no model, there was nothing. And then I thought, well, if I speak with colleagues and they are being asked, so what do you think about climate change? Then they go, oh yeah, there's broad consensus. So look at the IPCC kind of thing. And there's broad consensus in science that this is man-made and that it's happening. And then you say, how do you know? How do you personally convince me based on data, based on models, based on what do you personally know about this? And then that's basically it. So there's obviously consensus. Look at the papers, it's there, but there's no argument. So the question that I had was, can we do discussions in a different way? Wouldn't it be time to lead discussions in a way with actual arguments, ideally with computation, and how would we do this? So if we were to discuss something, say, about climate change or about any other kind of thing, malaria we discussed, and we discussed traffic accidents, road accidents, we discussed droughts, we discussed tornadoes, we discussed everything. So we ran this a couple of times. How would this go? And I don't think that we found the perfect solution. On the contrary, so we'd actually, this is more like a cry for help. Do you know of technologies, do you know of things we could add to this to make this work? So one of the things is we need to be able to program the entire thing in real time. So we want to be able to do everything live in a discussion. And usually the two of us sit in quite different corners of the world. So we use different technologies like Zoom, for example, to discuss this. We need to be able to exchange code. Stephen Wolfram said in the keynote that they are working on collaborative documents so that we can work on the same document. That would be a big deal. At the moment, we don't have this. So we try to use the chat system. If it works very well. But it wasn't necessarily stable enough for what we were trying to do. So that this is gone, I think I can now start this here. So where we are right now is that we discussed that this is wrong, so that what we see in this debate is wrong. And the question is, what can we do to improve this? And what we believe is that if we put the language into Wolfram language, that would be a good start. So can we speak the Wolfram language? Not in the sense of reading it out loud, but can we actually work with it? So my kind of feeling, the philosophy behind this is that at the moment, if you look at a computational essay, it's kind of Latin. It's the kind of thing you write down, you translate, you work with, and that's all fine, because it's much, much better than PDFs or static documents. But that's not how we use a language. So if you ask a Latin teacher, can you speak to another Latin teacher? They say, usually we can't, but we can write it out. So the whole trick is in speaking the language, using it. And this is what we've tried. Björn just spoke about our degree in Aberdeen, where basically all the teaching is live coding. We have problems, we want to live code, and we want to solve this. So in how far can we get analyzing these topics in real time? So basically putting the language into Wolfram language, speaking it. So at the moment, we came up with this here, which is kind of the setup I'm using right now, even though it doesn't work fully. So this is how it works. We've got one computer, which would be, say, my computer at home. We use a little gain capturing box, which is a cool thing that breaks the stream. Oh, come on. So there's another rule, don't touch it.
There you go.
There we go. Let me see where my talk comes back. Yes, there we go. So it's a little box.
Like this?
Like this. I don't touch it. And basically, it eats the output from my computer and puts it on a screen like here right now. This would be that screen. And it also moves it forward to a second computer, which basically is recording everything and streaming it to Twitch. So that we can basically, why do we do this? Because if I do everything on my own computer, on the laptop, and do then complicated calculations, it doesn't stream reliably. So now I have one computer totally for the streaming, OBS, so Open Broadcasting System, and we have the other computer that is free. Now that computer here is supposed to run Zoom, which means we can have a couple of people with Zoom calling in and using, for example, code share or other methods to share the code in real time. This computer technically would often have larger storage and perhaps GPUs for network training and so on. So if we had interactive documents we could all work on, this would look a little bit different. We don't have it. So basically, the person sitting at this computer acts a little bit like a moderator. They can either take the code via code share and paste it in a notebook, and you basically develop this notebook as you speak. Or alternatively, they can hand over control to any one of the other members, which is possible with Zoom or other technologies. So basically, this goes then directly to Twitch and to Zoom. We've done a couple of these discussions in the past.
We did, yeah.
And we can tell you more. Yes?
The Zoom process on the left machine.
Yes.
Isn't that also kind of...
It's not ideal, but it works.
It works. We tried other technology for...
Now what happens if you put Zoom on the machine on the right?
The problem is that, you see, the second machine, which would be this computer in this point, is basically completely independent. My Mathematica runs on this machine. They're not really connected. This is just like a
video
screen.
capture.
So if I had Zoom there and people would
to chat with you,
would chat with me, send me code via that system, it wouldn't work because I would be on the wrong computer.
But I thought that Zoom was just...
No. We got Alan Calviti on the other side.
So
and
right now we
we'll
have
be
someone
interacting.
else off-site who can contribute to this discussion. Okay. Of course, we wouldn't necessarily do this if we were sitting in the same room, but the idea is that we can do these discussions worldwide. So we have the setup. I can explain more about the setup if you want. And then we prepare usually for these conversations. And that means we have shared folders, Dropbox folders, and other things where we have data prepared. And
so basically what we do is what do we want to learn about or discuss in the next session, maybe next week or the following week? So we pick a topic, maybe it's a topic of conversation on the news or something that it's of interest for to investigate. So in this case, okay, we wanted to see the history of malaria and the cases where you have the cases before and what's going on now and find models. So
now this document is, or this data set is special because it contains the raw data. It also contains the steps of the data cleaning. And if you look at the very bottom, it would even contain rudimentary code here that allows me to represent the data. So basically, a person prepares this and says, that's a piece of data I would like to submit to this discussion. Thereby, I make it available for everyone to criticize. So if you don't believe my argument, there's my data. If you don't like my filtering, there's my data. Tell me where I'm going wrong, which makes this much more evidence-based than...
He will claim that this is manipulated.
Exactly. People might... Exactly. So what you could do, you could now go and say, well, if I think this is manipulated, give me another data set for this conversation, put it online, put it in the same format, and we'll have a look at it.
It's like a peer review of...
Exactly, of arguments, which is what we do in science, but this could be for any kind of discussion where you just open your arguments up instead of saying, oh, NASA manipulated this, or, on the other hand, showing a graph and saying, well, this comes from the IPCC, you have to believe this, because that's technically an appeal to higher authority. It's not he's right, it's not a scientific argument. And these discussions seem to be lacking arguments. So by doing it like this, perhaps we can open our arguments up and actually have them tested by friends and checking out what they think about this and say about this. So we try to stick to this kind of scheme that we clean the data in that way and say, raw data, this is what we got from the internet, there's the URL, so you can go to that URL, you can see what people did, you can manipulate the data, and you can agree or disagree with my representation of it. And of course, we make use of existing technology like the Wolfram Data Repository and other things, but it turns out that very often we bring in data from the outside.
yeah.
So here are a couple of, before we start, we try to do one later. But before we do this, we just wanted to show you a couple of examples of what we did in previous ones. We have recordings of these. The first ones are not particularly nice, I would say.
We were testing the environment and trying the different options on how to connect, so.
That's saying it very nicely.
Yeah.
Yes. Okay, so we have different things here. We have, for example, astroarchaeology. So this is a data set. We have LandViewer, which is providing satellite images, actually relatively recent satellite images. So if, for example, there is an attack on an oil facility.
This started with a conversation about the attack, the supposed attack from Iran on the Arab refinery. So, we were discussing this. How do we know what happened? So, okay, why don't we go and look at geoimages? And we know that there's a site called LandViewer that you can get up-to-the-minute images. So we pinpointed to that and obtained the data. And then we started looking at the structure, where the destruction happened, in what side, so from where could the missile come, that kind of information. And then Marcos stated, okay, I remember I read something on the newspaper today about the looting of tombs in Egypt. Why don't we take a look at the images around the Valley of Kings and Queens?
And this is actually called astroarchaeology now. So that is satellite data where you fly a satellite over a certain region, like all along the Nile. And you have this data not only in visible light, you also have heat and so on. So
radar too.
Radar, you've LiDAR for some regions as well. So you basically try to look for different light reflection or absorption. And if there are structures under the sand in Egypt, you see the structures lighting up if you do image analysis of this. So you're basically sitting in your office and you try to figure out where there are sites in Egypt and count buildings or something like this. This particular thing here is something, there's a scientist pretty popular for doing this kind of research. And what we did here, this is in Egypt, and that's a site where after or during the revolution in Egypt, looting happened at these ancient sites. So from the satellite images, you can see little bits where people dug stuff up, and you can count and you can see where that happened and how often that happened. So you can remotely monitor, even if you can't go into that country, you can remotely monitor what's going on.
We try to replicate the results of the paper. So we said, why don't we do it with Mathematica, see if what the paper shows we can replicate. And it was quite similar.
Yes, it worked. I mean, we then, because we deviate quite a bit, so you start talking about something, think you have a plan, but then the discussion, it's like a pub discussion, it just goes anywhere.
Yeah.
So there were things you could do with counting, because if you have different spectral bands, you can see whether trees are healthy. So we looked at olive trees in Spain or something like that, and you could individually for the trees find out that tree is sick and that tree is actually doing pretty well and things like that. That was one. This here is the vegetation. So basically look for change over the year in vegetation. And these are all things that happened during the discussion. So usually we try to limit this to an hour or 1.5 hours and end up doing it 5 hours or 6 hours. So very often it is actually long things. So road accidents in the UK, where we studied when these road accidents would happen, what time of the day, where they happen, and then because you've got all these nice technologies, so you can actually go to the individual roundabout and say, why do accidents happen? What do we think at that particular roundabout? You can actually walk around the roundabout with Google, and you can actually check what's going on. Let me see where I find another one. This is one we're going to talk a little bit about today. So this is climate change, and that's because I had that introduction with this, so what can we do computationally? So we try to do this basically for the remainder of the thing. We also had, for some reason one of us was interested in that, the crime statistics in Atlanta, where you shouldn't go and where you should go or can go. So it can be very practical things. You want to know about your city, you want to know about what your government is saying about climate change, whatever. Okay, so I think that this should be, let me see, yeah, that's that. Let's try one.
Why not?
So if you have, this was the Zoom and this is the code share thing. So the idea would now be that I open up a window with Mathematica, and I'm actually, the setup here is a bit awkward for me because I can't see what I'm typing, so I have to see what I'm doing there, so that'll slow me down a little bit.
Do you want to turn it around? No, you're connected, yeah.
So,
do you want to participate? We've got another computer. Oh, you're there. Yes.
So
and there's the Zoom, no?
Not in the Zoom.
Okay.
Well, you know, if you press F7, you can mirror the screen on that, so that you don't have two screens.
yes, I know, but I want this too. Because usually I would have two screens. So one is the one that's being streamed, and the second one is the one where I code, because I have to do coding as well. If I do that on the screen that's being streamed, I'm in trouble, because I can't actually work like that. So if it works, we put on that second bit here on this bit of the screen, we would put Wolfram Chat, for example. But at the moment,
is everyone Bayesian or frequentist in this discussion? Bayesians? Bayesians. Yes or no? Yeah. They are usually more.
okay, so let me see
I like
whether
cats, but they hunt mice. I don't care what color they are.
let me see whether I can make these look behind the curtain.
So you gotta,
So this would now be behind the curtain. So that would be what the moderator sees. And in this case, oops, that is this code share. Is somewhere on code share and can show me some code, please? Anything, just a plot of something. Okay. So that's very simple code. So if anyone is on code share, I should be able to see if you if you send me code. My code sharing is what? You think? Can you see that? So again, here's the code sharing. So if you go to the right code share, you should be able to type in.
Yeah, and that need to share your screen.
I need to share my, okay. Okay. Share my screen. No, you should just, if you type, I should see it. So it should be, you should see that on Zoom now too. Refresh it, okay. There we go. There we go. So I could now take this code. So if you were to say this is relevant for climate change, I'll just paste it in there. We could run it, and we could discuss this. Of course, Wolfram Chat would be ideal for this. But OK, there we go. So I think that Dero has some data to show to us.
Did you start
The what?
the data?
Cannot get into the server.
You should. People do get in.
Capital V, capital V,
Yeah.
that request.
5ZDQ37. OK, so do you have that? OK.
Not even code share is that stable.
Oh, there we go. OK, so there we've got all of this. So can't see. I have to move this to my side now. We're on the moon, climate change. Do you have anything, or can you not see it? Dero? I don't have the data. I mean, this won't run.
Downloaded it.
Nope.
Okay. So maybe I'll share it.
Yep. I already put this data there. So what we try to do is we try to get data in here. Yep. OK, then what about while Dero is doing that, let's start with something I've got here. So I'll delete this. And let's say once we have the data and we analyze the data, one of the things you might want to do is you want to predict on the data. So one of the things you can do is you can look at a simple model. And this is a model that we hopefully will be able to implement while we're talking. So there is a model here that I can open. So it opens a website. And this is something you would, for example, find during this computational conversation. You would see, OK, here is a model where I can say how much CO2 we emit at any point in time. And you can move this forward. And based on this, basically kind of try to predict what's happening in the future. And what they do, there you see kind of based on how much CO2 I emit. It's the emission. Now the CO2 level in the atmosphere would go up, and that means that the temperature goes up. And what they've done here, they've actually made a really, really simple model that is actually called a very, very simple model. And if I give you this link here, so let's go here. Click here. So then you have the model, and you actually see the equations as well at some point there. And you have also different IPCC scenarios. So what this model basically does is the following thing. We first want to clean this. And again, it would open my model up to criticism. So I clean all this kind of the data. And now I put a couple of things in. I'll tell you what this means. So this model says we have certain parameters. We have a temperature in 2010, which is 14.6 degrees. So this is here. And this here will be the CO2 level in 2010. We have a couple of parameters for this model. And this is the emission. This is basically just the emission of carbon dioxide. This is actually just the carbon part of the emissions. And we have a value for the degradation of the carbon dioxide. So basically, what I can do now, I need two equations for this. And these two equations go right here. So I've got the CO2 level. And that is the entire equation that this model does for CO2. So it basically says there's 1 minus degradation, so there's a certain fraction for the degradation. And the next CO2 level depends on what I put in the atmosphere right now. So I've got the emissions here. And it turns out that if I have 2.3 gigatons of CO2 in the atmosphere, that would increase the level of molecules by 1 part per million, so 1 ppm. And this is where this 1 ppm comes from. And again, you could now, in the discussion, this is what we did when we had that last time, you could say, why? I don't believe that. Why is 2.3 gigatons actually 1 part per million? And what you can do is you can ask Wolfram language directly, say how much atmosphere do we have, natural language input. It gives you the amount of atmosphere, and then you can basically just calculate what 2.3 gigatons of CO2 do. So that's the first thing. So this would allow us now to make a kind of list of what CO2 does. And the next equation would be how does the CO2 influence our temperature? And this is a very common law. So you have the S log, so it's a logarithmic law. And this is the ratio between the CO2 levels right now and in 2010. And with the parameters I've given you just here. So once this model is there, now it's up for discussion. Of course, this model has lots and lots of flaws. It's very simple. There are all sorts of feedback effects which are not considered, and people could just criticize this. And if I run this, so simple a dateless plot. Oops. CO2. What have I not done? Degradation.
This is a recursive definition.
It is, yes, exactly. It should be. It's a recursive definition. Yeah. If I have the CO2 level last year, I can calculate the CO2 level next year by knowing how much I emit and by how much is degraded. So this here, in that case, would be a very, very simple model or a very simple assumption where I say I have the same level of CO2 being added to the atmosphere over time. So I can now, of course, plot other things such as this is temperature. So I can see under this scenario how would the temperature behave. And again, you could criticize this.
Yes, and with the technology, when it works, we can pass code along. So what we'll do now is Marco's gonna release the share of the screen, and I can show
Yes.
some other things on this side.
Okay, that's good. So I will remote control
Stop sharing,
and
or
this is
give me
demo.
if you can give me the, can I cut and paste there? No.
You should be able to control my screen now.
No, if you can let me
Okay,
share
okay,
the
okay.
screen.
All right. Stop sharing.
So as Marco was saying, he was discussing the emissions of. Are you
Yes,
seeing
I
it?
do this.
Maybe you can move that to the
Yeah.
other screen. Fantastic. What we do is we do share the data content. So for example, in this example, I'm going to focus on the ranking of countries based on their emission. And we can see that 30% of the emissions of carbon in the atmosphere is done by China, second the United States. You see the ranking by people. So you know that to get a
Also, can you double click the Zoom session?
You can double click the Zoom session, yeah.
double click the Zoom session. Okay. Is that better? Okay. Let me try this. Better? So any effect on the global amount of emission in the atmosphere needs to come from the top level countries, right? If 30% comes from China and then 15% from the United States, then India, that's where the focus should be. It's also interesting that you can look at the emissions by country. So for example, because we have all the data there, we can start taking a look at the details and the history of each country per se. So by exploring, for example, the United States since the 1900s to today, this is the total amount of emissions of carbon. This is liquid, so this is gas. You can see interesting things from history. The oil embargoes in the 1970s. Consumption goes down of gas, fuel. This is basically coal that keeps going up and up until this time in which fracking starts. And in the United States, we're replacing the energy from coal to gas, which lowered this emission. So you see that this emission is coming down, and it's being replaced by gas. Another interesting thing is that many countries
There is one thing, so these are emissions,
of carbon,
but only those that come from burning hydrocarbons.
burning hydrocarbons. Yes.
What about like the ones that come from agriculture, from
Those are not. In this data set, it's only on that. So we're looking burnt.
Like because I think that there is a big component. That
There's
is
a big
like
component on that one, but you have to.
production of,
Yes.
concrete,
Yes, and there's other ways to measure that. So, but this data set is what about the consumption? Not on agriculture, but on consumption. It was an interesting case here that if we look at China, right? So we have been moving manufacturing of goods to China. Look at since 2000, the growth, not only in their manufacturing, but also in their infrastructure. Building steel and building cement requires a lot of energy. Calcium carbonate for the lime to build. And as you can see, most of that carbon comes from coal, so solid consumption. Energy is necessary for any society to move. So if there is a solution, we need to find a solution on the coal that is being burned. So one of the alternatives, although it's discussed by many people, is, move to Gen 4 nuclear energy. And that's what Bill Gates was trying to do on getting that first reactor being built in China, because it attacks that main source, which is solid radiation. Then we did all kinds of other analysis.
You now go also back, by the way, because if, as you say, there might be other sources of CO2. So for example, oceans also. So how much CO2 do they capture and store?
Yes.
And that you can then, of course, compared to historical records on the model that I just presented, and see that it fits in certain ranges pretty well. So for the situation right now, it actually fits very well. But if you go back in time, if you take paleoclimatic records, it doesn't. So because other effects might be relevant, so you can actually check whether the model is valid for this or not.
So for the example, this is taking the, we looked at all the records for paleoclimate, the Vostok, ice analysis, and also getting data from NASA on the irradiation. So the yellow line is the solar irradiance, and this is basically calculated based on the Milankovitch cycles. You can go forward and back in time. So this is the amount of energy going in, and the blue line is the delta T temperature, and this is carbon. So you can see in certain areas or certain times, if you see the correlation, as you say, right, between CO2 and temperature, most of the time it does, but there are certain paths that on this a complex system it goes through that it's not necessarily the force that it's driving the temperature change. So these are the things that you can observe by looking at the data. You can look at, for example, we did a study on the energy of the hurricanes, accumulated cyclone energy trends. So you can see how much energy was released by the hurricanes in each season, accumulate that, do a linear plot, and show the results. So this is by looking at just the data. Hopefully by integrating the signal, if there is a change of angle, you will see that there's more or less. And it looks pretty much aligned. So this asks questions, okay, is that really, is there more accumulated energy in storms being generated? And this is, all the data comes from NASA. Tornado analysis. We looked at, for example, the tornadoes. There's a database with all the tornadoes going back in time. And
so usually when the technology works, this is basically what's being programmed as you speak. So these are kind of typical outcomes of discussions that you would have and get out.
I'm giving you the control back.
And then if the control comes back, let me see how I can do this. Let me see, exit full screen. So what I would do now, I would take these records and would say, here I've got data about CO2 levels. So I take Viro's data and say these are the CO2 levels. You see here it's about below 250, and this is from the year 0 basically to 2000. You see the change in CO2 levels, and based on the model, I could now say, okay, what does that mean for temperatures and so on. I can go through the climate models and the CO2 emission scenarios that the United Nations have, and I can just visualize this and try my own scenarios out. And what you see is if I compare my model predictions to the actual data that Diego had, I can see that this is basically the kind of things I see from about 1900 up to now. This is the blue data is measured, and the orange kind of thing is what the prediction is. And the interesting thing is that for this, it fits more or less, it predicts the trend. I can go into the future, so follow my equations, what they would say for the future. I can look at with a round here, at the prediction error, so I can try to figure out what, if parameters are not perfectly known, where would we go? But then I can go back and critique my own model, because I don't trust it. And I can basically take paleoclimatic data. So this is CO2 levels on much, much longer time scales. And what you see then is that you have these very, very large fluctuations. We also have data about the temperature in these times. So I can basically compare data and so temperature and CO2 levels. And now the cool thing is I could, of course, plot this one versus the other to figure out whether my model works. Because if my model predicts the relationship between CO2 and temperature, so this is a double axis plot, it's a resource function, where you have the temperature on the right-hand side and the CO2 levels on the left-hand side. And of course, you see a clear common pattern here. But the model is only built for a certain type of situation. So if I run this on the model, you see, well, I get kind of this, and then there are large excursions, which basically are kind of these guys here, there and there.
So we did try working on a collaborative environment. We tried Wolfram Chat in several sessions. That didn't work. Code Share IO, we were only 2.
Yeah.
It worked fantastic. It seems that now that we put more people in, it does have some issues.
But I think the interesting bit here is that, for example, you see that that's kind of the red line is the curve that our model predicts, the connection between CO2 levels and temperature. The old records would show you that kind of the blue kind of stuff, and that doesn't look at all like the red ones. But in the kind of region where we currently are, so there is it seems to correspond. So it's made for this particular situation, which again is interesting because if you say that the models predict that CO2 will go up an awful lot, but the model is not built for that particular situation, then of course the predictions get awfully wrong.
And then you have to ask yourself about the model too, right? Because it should work. We know there are other components that would also talk about those changes in climate. So which are those components? Are those active or not?
And you could, I mean, because you have all this interactivity in Mathematica, you can build these kind of manipulators. I hope that this runs now. I can't see whether it's doing anything. No, it's not. Where you can actually look at different emission scenarios and manipulate. Oh, there we go. And you can say, this is the time when my climate policy set in. So if I change at a certain threshold, and you see the x-axis there, and I say I decrease, for example, my output with a certain percentage, and you can say, depending on where I start decreasing it, so I decrease my output, you see that has an effect. And if I decrease it later and later, that'll undo this to a certain kind of ratio. So I can basically study with manipulate different scenarios for how I change my emissions in the future and when I start doing this. And you actually see that if you go about 30 years in the future and you reduce it much, much more basically to 0, that we still do not, certainly not meet these climate kind of targets. So in combination of the data and the model, you can then decide what you believe is true about this. Okay. So there we go. And here are, so to compare then our kind of model where we can shift kind of our emission scenarios. This works, by the way, this is when you program live, you see that when you do the same thing with units, it's too slow for a manipulate, so we just do that without units for this. And that's basically the biggest problem. So how do you get this fast when you run it? But then we also looked at a number of emission scenarios that they suggest, and you basically plug this into your model that's there and can kind of see how these would basically pan out in the future based on that model. So what we have, if you have better ideas about the sharing the code, because at the moment the code share, I mean, it usually worked for us pretty well.
Yes.
The Wolfram chat system was a little bit too unstable for longer conversations, even though it's good because you have got the sliders and everything in there directly, so that's certainly an advantage.
It was really easy to, for example, with code share, you cannot send objects like a data set or a time series. There's no translation. So, but in the Wolfram chat, it was really easy.
Doesn't it paste the input form?
We need to try.
What was the question?
If you just drag it.
No, drag it, copy paste.
Okay, or copy paste, we can try it.
Copy and paste. Well, you can basically also directly to manipulate. You can copy in if it works. So if you just have an output in form of manipulate, you could just plug that directly into the chat and it works.
Yeah, it could be input or output.
Yeah.
Both.
Yeah.
Let me try.
And then what we can do, because this didn't work with the streaming.
That's Tali's fault. That you cannot copy a data set?
Well, you can even do one
I
thing.
just
we
seen
did,
that in code share.
we did a couple of times, and this is you can share the kernel between your main notebook and the chat system. That means if you have variables in there, they work directly in the chat system. And you get a nice transcript.
The problem is that data that if you try to copy the out, it censors itself. So you have
Yeah.
the input form to be able to.
Yeah, but with the chat it was really nice because we could actually put that straightforward and you could see it. So
Okay.
so what are the takeaways for us on all the conversation? What did you experience?
So what we
during
can
our
do is we
talks?
can show you a couple of videos, because we've got videos of the ones we did with a more set up environment, and we can share these videos, so we can put them on and let you see what we've been up to. And I think actually it turns out that the most complicated thing is not the live programming, but it's basically the technology to exchange this for the remote collaboration. That's a problem, because that's not fully implemented in the Wolfram language, I guess. And I think what we tried is that usually if you do this, it's about one moderator and 2 people or 3 people discussing is ideal, because then you have one who can manage the system, and you've got 2 or more people actually leading the discussion, which seems to be a good compromise there. Do you have any questions?
Thank you.